Derivative rules: power, constant, and sum or difference. Let's look back at a few of the derivatives that we have calculated already. We have found that the derivative of 7x squared minus 3x is 14x minus 3. We found that the derivative of 10t squared is 20t, and the derivative of x cubed plus x squared minus 2 is 3x squared plus 2x. What observations can you make? Do you notice any shortcuts for finding these derivatives? Notice that the 7x squared became 14x, and negative 3x became negative 3. In our second one, 10t squared became 20t. In our last one, the x cubed became 3x squared, the x squared became 2x, and the negative 2 became 0. Notice the power of each term decreased by 1, and the coefficient was multiplied by the original power to get the new one. So 7x squared became 14x to the first, or 14x, and negative 3x became just negative 3, x to the 0, and anything to the 0 power is 1, so it goes away. The derivative of 10t squared is 2 times 10, or 20, and then t raised to the 2 minus 1, or first power. And the derivative of each term here, x cubed, became 3x squared. X squared became 2x to the first, and negative 2 became 0. At this point, you may be asking yourself if there is a more efficient way of finding derivatives, since both forms of the limit definition of a derivative can become tedious to use. In our exploration, we noticed a pattern that occurred with a function and its derivative. Mathematicians also noticed these patterns and created the derivative rules from them that we now use to simplify the process of finding derivatives. Once we memorize these rules, we won't need to use the limit definitions as much as before. In our exploration, we found that any of the constant terms of the function were gone in the derivative. So the constant rule that the mathematicians came up with states that the derivative of a constant function is 0. So if c is a real number, then the derivative with respect to x of c is equal to 0. And this can be confirmed graphically because a constant function is a horizontal line, and therefore it has a slope of 0 everywhere within its domain. That's why the derivative of any constant is 0. The exploration also showed us a pattern to finding derivatives of terms with real numeric exponents, and that's the power rule. The derivative of a function f of x, which is equal to x to the n power, where n is a real number, then f prime of x, or its derivative, will be equal to n times x raised to the n minus 1 power. For example, the derivative of f of x, which is equal to x to the 5th, is f prime of x, which is equal to 5 times x to the 4th power. In other words, what's happening is the 5 is being brought down as the coefficient, and 1 less than 5, or 4, becomes the new exponent. The power rule extends to functions that have a constant multiplier as well, which brings us to the constant multiple rule. The derivative of a function multiplied by a constant c is the derivative with respect to x of c times f of x will be equal to c times f prime of x. For example, we have f of x is equal to 2x to the 6th. Then f prime of x is equal to that constant c out in front, and then we're going to multiply by the derivative of x to the 6th, which will be 6 times x to the 5th. So again, our c value that we have in this original problem is the 2. So I'm going to replace the c with the 2. And now we can multiply these two values together. 2 times 6 is 12. And we have x to the 5th as our final derivative function here. F prime of x is equal to 12x to the 5th. The power rule also extends to functions that have a sum and/or difference. So the sum difference rules states that the derivative of a function y equals f of x plus or minus g of x, where f and g are differentiable, is that y prime is equal to f prime of x plus or minus g prime of x. For example, the derivative of y equals 2x to the third power minus 5x to the second power is y prime is equal to, we take the 3, multiply it by the 2 to get 6, and then we lessen the exponent by 1, so we get 6x squared, minus 2 times 5 is 10, and 2 minus 1 is 1, so we have minus 10x. As you may be guessing, not all functions will be in the form where it will be obvious which rules we will need to use. Sometimes we're going to need extra steps included within that process. Let's look at a few harder examples. Find the derivative of f of x is equal to x times x plus 4. The first step is to distribute the x outside the parentheses to both terms. So therefore, f of x is equal to x squared plus 4x. And after we finish distributing the x, we can actually work on determining the derivative, or f prime of x. And we're going to use the power rule for this first one, 2 times x raised to the 2 minus 1, and then plus 4 we already have there. This x is being raised to the first power, so 1 times 4 is 4 still. And then we have x raised to the 1 minus 1. And then if we simplify these, we will have 2x to the first power plus 4 times x to the 0 power, and x to the 0 is 1, so it's just 4. Let's try to differentiate f of x is equal to 3x to the 4th minus 2x squared plus 5x, all divided by x. We're going to begin by dividing each term by x. So we could rewrite this as 3x to the 4th divided by x minus 2x squared divided by x plus 5x divided by x. And when we simplify it, f of x is then written as 3 times x to the 3rd minus 2x plus 5. Now we can differentiate the simplified version of f of x using the power and sum or difference rules. And when we do that, we will get that f prime of x is equal to 3 times 3x to the 3 minus 1 minus 2 times x raised to the 1 minus 1 and plus 0, because the derivative of any constant term is 0. And then if we simplify this, we will get 9x squared minus 2, because 1 minus 1 is 0 and x raised to the 0 power is 1. It is also important to note that since the original function is undefined at x equals 0, because there's going to be a hole in the function, because there was that common x factor that we simplified or canceled out in both the numerator and denominator, that's a removable discontinuity or a hole. So the derivative will also be undefined at this point, x equals 0. Given the function g of t, which is equal to 1 divided by t to the 4th, what is the derivative? Begin by rewriting g of t using the rules of exponents. 1 divided by t to the 4th is equal to t to the negative 4th power. And then apply the power rule. take the negative fourth power, rewrite it in front, so we have negative 4 t to the negative 4 minus 1 for g prime of t. And then if we simplify that, it becomes negative 4 times t to the negative 5th, which can be rewritten as negative 4 divided by t to the 5th. Please also note that since the function, the original function here, is undefined for t equals 0 because of that asymptote, the derivative is also undefined at that point. Let's try one more. Find the derivative of f of x, which is equal to the cubed root of x. Begin by rewriting the cubed root of x as its exponential form, which is f of x is equal to x raised to the 1/3 power. Now we can apply the power rule to differentiate. So f prime of x is equal to 1/3, bring that power down, and then we have x raised to the 1/3 minus 1, or 1/3 times x raised to the 1/3 power minus 3/3. And when we do the subtraction here in the exponent, we will get x raised to the negative 2/3. And then because this is a negative exponent, we can move it to the denominator and then also put it back in radical form. So that would be 1 divided by 3 times the cubed root of x squared. And note, since the function is undefined at 0, x equals 0 because of a vertical tangent, the derivative is also undefined at that point.